Hey, some more 3-2 problems. I'm getting kind of sick of doing all these, like, really algebra-heavy ones. How about you? Well, I'm glad that you're getting sick of them because in 3-3 to 3-6, we're going to learn a whole bunch of rules for how to do derivatives with more ease. But before you learn how to run like the wind, learn to walk like the what's the thing in nature? If wind runs, then what's the thing that walks? Walk like the, not rain, rain falls. I don't know. If you have an idea there, let me know. I'm curious. I don't really know. Okay, so 5 here, before we get into all the algebra, sketch the graph of a function f for which f of 0 is -1, f of 0, okay, I'm going to plot these points first. I lose track of what I'm doing. So f of 0 is -1. F prime of 0 is 0. What does that mean? It means the slope, as the function passes through this point, it has a slope of 0. I'm just going to make a little, like, sort of sketch there. It doesn't mean it's a horizontal line there. It just means that the tangent line would be horizontal. So whatever it does something like, I guess it could go like that. Somehow when it passes through here, it's flat at that instant. Okay, so f prime of x is less than 0. So the slopes are negative when x is less than 0. So that means, like, on this side over here, the slopes are negative. And we want to read functions always from left to right, just like we read words. So that means it's going to be, if the slopes are negative, it's going to be coming down. And then when f prime of x, the slopes are positive on the other side. So the slopes are negative on this side and then positive on this side. Something like this. Could be a parabola, could be some other thing that looks like that. All right, cool. How about 6? Same idea. So f of 0 is 0, goes through the origin. And when, let's see, f prime of 0 is 0, so it's horizontal again there. And f prime of x is positive on both sides. Okay, so as we read the function from left to right, that means it's going to be increasing on both sides. So could it be this? Straight line through there? No, because it has to have a slope of 0 here. So I guess it must have increasing slopes and then, like, flatten out just for an instant. And then instead of turning around and having negative slopes, it turns back up. And if you were looking for a function that has exactly those characteristics, y equals x cubed does. It does exactly that. All right. What are we jumping to now? Number 15. Okay, so in the directions, they say use formula 12, and forget about the formula 12. Like in the problem, there's a problem yesterday, 27 and 28, I think. One of them, they threw a delta x in there. So forget about that whole number 12 thing. That's just the same as the this. And this is what I want you to use. I don't know why our book's all excited about that delta x thing. So that's what we're using for 15 through 20. And so exactly like the problems that we did yesterday, except you don't have to find a tangent line at the end. And the other thing that's confusing, maybe, is that they say find dy dx. So remember, I think in the notes somewhere at this point I've told you that f prime of x, we also call this dy dx, where the d's are reminiscent of, like, change in y, change in x. Reminds us of slope, dy dx. And sometimes we also write, since, like, f of x and y are the same things, right? Sometimes we write y equals x squared, and sometimes you write f of x equals x squared, and we think of those as being the exact same thing. So if we can write f prime of x, we probably want to also be able to write y prime. Just like these are the same, we'd like to be able to do that. And we do. So this time they're using this notation, saying find this, but it's the same thing that we were doing. All right, so let's jump in here and do it. First one, 1 over x. So I want to find dy dx is equal to the limit as h approaches 0 of f of x plus h. That's what 1 over x looks like. And then I'm going to multiply the top and bottom of that. Or you could do the common denominator thing, whichever way makes you the happiest. I say which one makes you the happiest because it's possible that neither option makes you particularly happy, but one maybe might make you less sad. So when you multiply this by that, I get x. When I multiply this by that, x is going to get minus x plus h. Good parentheses management is important. Should I distribute this stuff? Nope. Because if you did, you're going to, well, you're just going to have to factor it out again. So h times x plus h. This is a borderline skippable step here, if you feel confident. You can write out more steps if that makes you feel more confident. And if you had this one written out, then maybe this would be skippable. I don't think you could skip both. Just want you to be happy. Okay, so there's the derivative, and no tangent line this time. So that's it. All right, 16. So the limit as h approaches 0. I'm doing 1 over x plus 1 now. So that, I think that should feel awfully like this one, shouldn't it? So 1 over x plus 1 minus 1 over x plus 1 all over h. So same thing here. I just need to multiply this time by x plus h plus 1. So x plus 1, top and bottom. So let's see, when I multiply this times that, those cancel and I just get the x plus 1 minus, and then I just get this, x plus h plus 1. Now my h, x plus h plus 1, x plus 1. Let's see, how much can we do in one step? I don't know, can we get to the answer from here? Maybe? Let's see. I think maybe we can. The x minus x cancels. 1 minus 1 cancels. Minus h, but I know the h is going to cancel out with that h. And then when I plug the 0 in for h, I get x plus 1 times x plus 1. Oh, that was bold, going straight to the answer from there. I think you could do it if you feel confident. You don't feel pressured into leaving any steps out. Just want to give you options. All right, so 17. Looks like I got some polynomial action here. So x plus h squared minus x plus h. Got to be careful that you plug in the x plus h for all the x's if it shows up more than one place in your functione. All right. Let's see what's happening here. I think there's definitely some algebra I need to do here. So here I got to FOIL that out. X squared plus 2xh plus h squared. I'm going to distribute that minus sign. I'm going to distribute this minus sign. Okay, there's going to be a whole bunch of stuff that cancels out here. So very carefully. Got x squared minus x squared. Those cancel. Plus 2xh. That does not cancel. plus h squared. That does not cancel. Minus x plus x, that cancels. Minus h, that does not cancel. All right, that is super important, obviously, that you don't mess that up. So I'm going to factor an h out now. Borderline skippable step here. 2x plus h minus 1. Of course, all these steps are skippable if you're skipping them and getting the right answer. If you're skipping them and not getting the right answer, then, well, you got to reevaluate. All right. Boom. There's the derivative. All right. New page. Let's see. We are on number 18. Oh boy. I'm going to bust out my Pascal's triangle right about now. Let's see, that's x to the 4th plus 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the 4th. All right, and it didn't really matter if if I messed up anywhere back here, because all those things are going to have, they're all going to get knocked out by h's turning into 0. So let's see, the only thing that cancels is the leading x to the 4th. Then I got, factor an h out, 4x cubed, factored an h out, so each term is going to have one less, one fewer h. Okay, h's cancel. And then all this stuff gets knocked out by h's that are still hanging around. So it's 4x cubed, which is off the screen. There it is, 4x cubed. All right, 19. 1 over the square root of x. Ooh, this is like a conjugate and rational expression. That's mean. So 1 over the square root of x plus h minus 1 over the square root of x. Really not that bad. Just have to do a couple of things here. All right, so let's see. What should we do first? It doesn't really matter what order you do things in. The things are, we have to resolve the fraction issue, and then we have to resolve the square root issue. So we're going to have to do the multiplying by the conjugate thing and the multiplying by the common denominator thing. So I think I'm going to scribble this out. I think I'm going to do the multiply by, I think I'm going to get rid of the fractions first. That feels like a good idea to me. Of course, sometimes things feel like a good idea, and it turns out they're not. But I think this is good. I think we're good here. But that's okay. You know, you got to be not afraid to make mistakes, especially when you're doing math and science. You have to be willing to try something when you're not supremely confident that it's the right thing to do. All right, so when I went through there, my square root of x plus h's, those canceled. I got square root of x, and then ditto likewise. So let's see, in the bottom I've got all this junk. Not going to try to simplify at all. Okay, so now what? Okay, so now I've got square roots. I don't have any fractions anymore, but I've got to multiply by the conjugate of that. do you think about the expression, if I told you to do this carefully, so you didn't make any mistakes? Think about that expression sometimes. To do something carefully, it kind of implies that you have to care, right? If you're doing something carefully, then you're like full of care about the thing that you're doing. So I think it would be fair for you to say, you know, when you're knee-deep in this algebra, and I say do it carefully, and you're like, well, actually, Mr. McGrath, I don't really care that much about this. And I understand that, if you don't care about this. But you need to care, because if you don't, if you just go through this and you're like, oh, make it stop, I hate this, when is this problem going to end, then you're going to get it wrong. And if you do it carefully, then you're going to get it right, and it'll actually be less painful to do if you actually care and pay attention and, you know, try to get all the little details right. So the good news is that caring about it, you can totally fake that. Like, you can totally like pretend that you care, even if you know, like, deep down in your heart that you don't care. You can totally fake it, and it works. It's like the thing where, you ever seen the like research? It says, like, if people smile, if you smile a lot, it actually makes you physiologically happier. Even if you're totally faking it, it does work. So there you go. Same thing with math. You just have to pretend that you care. Okay, so I'm going to, the x minus x, that cancels, and then I'm going to end up with a minus h here. The h's cancel, leaving a -1 on the top. So that's gone. And now what's going on in the bottom here? When the h goes to 0 here, I have square root of x times square root of x. Okay. When the h goes to 0 here, I have the square root of x plus the square root of x. Right? And you could leave it like that, and I'm pretty happy about that. That's me. My messy COVID hair, being happy about that. Probably wearing a baseball cap most of the time if I'm not at school because my hair is so messy. Look, I'm happy about that. But you could also, if you wanted to, you could exercise some of the, if you went back and did any of that skills practice stuff that I posted, kind of review materials that were optional. This is x to the first, and this is x to the 1/2. X to the first times x to the 1/2 is x to the 1.5, or x to the 3/2. And then you could write that, and since that's on the bottom, you could write it like this. That would be an option. And I'm not doing that just for giggles. There's a reason you can file that away, like writing it like that. Pretty soon, that's just going to be the way that we write these things, because it's going to be easier for us to do it that way. You're really going to make me do number 20? I mean, it's the same thing. Oh, man. Okay. Nope. See, look. I'm going to set a good example. I'm going to pretend that I care about this problem. And, you know, I do care about this problem, but I care much more about you doing it than I care about me doing it. That's the problem, I guess. I've done this problem before. Been down this road before. All right. Oh, got to do this first. Okay, so my common denominator, or my denominator removal thing, is going to be that. All right, look at me caring. So I multiply here, those cancel out, and I'm ended up with, I don't think that's good English. Multiply this by that, and then I'm ended up with that. And then on the bottom, I'm ended up with the whole big mess. All right. How much can we do here? I got to multiply by the conjugate now. So I don't think that I can skip writing this out. I think there's just too high a risk of making a mistake if I try to shortcut this step. Okay, so let's see. Where are we at now? X minus 1 minus parentheses that thing. Alright, now I feel a shortcutted step coming on here. I think the same as what we did in the last one. So I think we're, it's always darkest before the dawn, or is that an expression? So like things have, like, this algebra has proliferated into an awful mess here, but soon it's going to clear up a lot. In fact, I think this is really the last messy step here, because I think I'm going to try to get all the way home from here. Okay, so let's see. X minus x, negative 1 plus 1, minus h. Now the h is going to cancel. We all know that. So I'm going to write that minus 1. And there's the h that canceled with 1 on the top. Okay, now in the bottom, these h's are going to go to 0. What h's are remaining? So here, that's gone. X squared to x minus 1 times square root of x minus 1. It's just x minus 1. And then, just like the last problem, that goes to 0. I've got 2 of these. 2 times the square root of x minus 1. Same deal as before. You want to leave it like that? Great. You want to get all fancy? Not really fancy. X minus 1 to the negative 3 halves. Woo! All right. I think there's a couple more we're supposed to do here. Looking at these graphs, 23 to 26. 23 directions on the very bottom of page 187. Match the graphs of the functions with the graphs of their derivatives. Interesting. Okay. So, I don't know if I'll write the answers for this. Maybe I'll just, because you have it in the back of the book, maybe I'll just point and talk here. So, these are the graphs of the functions, and these are the graphs of their derivatives. So, let's not even look at this. So if this is a function, it looks like it has, it's like piecewise linear, right? So it's got this piece, which has a constant slope, and then this, which has 0 slope. So we would be looking for a graph of the derivative that was constant for a while, which would mean like horizontal, has the same slope, and then dropped down to 0. And there it is. So slope is constant for a while, and then it drops down to 0. And it looks like at that sharp corner, there is no, like we can't define a tangent line when there's a sharp corner there. All right, this one looks like I have constant negative slope, constant positive slope, constant negative slope, constant positive. So constant negative slope, that'd be a little horizontal line somewhere in the negative, and then a little horizontal line in the positive. So it's going to be like a little steppy up and down function, like this. Negative constant, positive constant, negative constant, positive constant. Okay, how about this? I've got something that, it looks like it's pretty flat here, so it's going to start out like at 0 or close to 0, and then the slopes get bigger, but then decrease back to 0. So this is 0, right? So I've got something that starts out around 0, gets positive, but comes back to 0. And it looks like somewhere in the middle there, it would be that's like the steepest it ever gets. So there would be like a little peak in the derivative. And then it looks like the slopes get negative for a while, then there's the most negative, and then come back to 0. So if you were trying to sketch that, I'm looking for something that it starts close to 0, goes up into positive territory, comes back to 0, goes into the negatives, and then comes back to 0. So something like this. And now it looks like B. If that made your head hurt a little bit, we're going to have lots of practice looking at graphs like this and sketching derivatives. It's a really important skill, and we'll have plenty of practice. And this is really like this is super early days, so if this seems hard, that is okay. Don't uncover those. So here in D, looks like I have something that starts out around 0, goes into the negatives, and gets like really big negative. So it starts out around 0. Let me grab a clean sheet. Starts out around 0 over here, and then gets negative, and it gets like really negative. It looks like it might even be like approaching some kind of negative infinity, something going way down like that. So it kind of looks like itself there. That's interesting. And then on the other side, it looks like I have something that starts like super positive, like that's almost vertical positive. So it starts like really high positive slope, and then is coming down. These are still positive slopes, but they're getting closer to 0. So the slopes are they're still up here in positive territory, but they're getting closer to 0. So something like that, kind of like 1 over x, I guess. There it is, C. And then how about this? Something that's like starts close to 0, gets positive, and then comes back to 0. It's never negative. This thing never has a negative slope. It's close to 0, but positive, positive, close to 0. So something that's like close to 0, gets positive, and then comes back down, but is still like close to 0, but not negative. So something like that, like a bump. There it is. And there, how about that? Well, I guess it's the only one that's left, but should we talk about it? Sure. So here, it looks like if this is like a semicircle, then right at the edge here, the tangent line to that actually would be vertical, so it would be undefined. And then there's super positive, like very steep positive slopes, if you imagine all those tangent lines, going down to 0. So real big positive numbers going down to 0, and then going into negative numbers, negative, and then getting close to negative infinity again. So that's that. Geez, that looks like the tangent function, except upside down. That's interesting. All right, so that's a tricky thing to do, I think, but it's important. All right, in number 24, I don't think there's ever been a year where students didn't have trouble figuring out what the heck to do with this. So if you feel like you didn't know what the heck to do with this, that is okay. Got lots of company. So the trick is here realizing that that function is the top half of the unit circle. It's not by accident that I asked you to do, if you went back and did that like graphing practice and stuff, the review stuff, made that all optional because we were not allowed to require summer assignments, but hey, you should look at that stuff. It's important. So this is a graph of y equals the square root of 1 minus x squared. It's not just the top half of any circle, it's the top half of the unit circle. And they want us to make a geometric argument to find f prime of the square root of 2 over 2. That's a nice point on the unit circle. In fact, I know that on the unit circle, the point right here, this is square root of 2 over 2, square root of 2 over 2. And I know that happens at 45 degrees, or pi over 4 radians. And that's a 45-degree angle. So let's see. If you want a tangent to a circle, and this is a radius of the circle, the tangent line to a circle is perpendicular to the radius. Geometry fact. How about that? So if the slope of this, I mean, what's the slope of a line at 45 degrees through the origin? The slope's 1, right? The slope is 1. So then this perpendicular line would have a slope of negative 1. So f prime of square root of 2 over 2 is negative 1. So the geometric argument is just realizing that's a circle and it's just a tangent line to a circle. That's all. 25, 26, we want to sketch some more derivatives, like what we were doing. You've got the book in front of you, presumably. So I'm just going to sketch the derivatives. So that first one, what's the slope of that? It's 0 all the time. So it's just that. How about the slope of b? Let's see. I got two lines. I got a line segment that has negative slope on the one side. It's got negative slope. It's a 30-degree angle, so I think you could actually figure out what the slope is. Couldn't you? Isn't it like negative 1 over the square root of 3? If you did a little bit of trig, whatever, but it's some negative number. And then there's the 45-degree one, so the slope of that would be negative 1. So that's what the derivative would look like, two negative constants. C, let's see. Starting out, I'm reading the function from left to right. So it starts with a very negative slope, right? Very steep negative. I'm just going to kind of start sketching down here. It comes up to, by the time I get to negative 1, it has a slope of 0. The tangent line at negative 1 would be horizontal. And then it looks like it gets positive. The slopes are positive, right? Like up in here. And then at 0, the slopes are back to 0 again. The slope is back to 0, right? If you tried to make a tangent line at 0, that tangent line would be horizontal. At maximums and minimums, tangent lines are horizontal, which means the derivative is 0 at those places. That's a smooth maximum and minimum. There are problems with things like the absolute value function. Does this have a slope of 0 here? No, you can't draw a tangent line there, and the derivative is undefined because it goes very abruptly from one thing to the other thing. And if you wanted to get technical about it, because the derivative is defined in terms of a limit, the limit is not the same on the two sides, and therefore it does not exist. So, what's the slope here? Does not exist. The point on the function does, of course, and there it is. But anyway, so in C, again, when we get to 1, we get another 0 slope, and then we go into positive numbers. And then between these, the slope is positive, and between these, the slope is negative. So that. And if you want to make a connection back to a problem, I think we did in this assignment, this looks kind of like it could be like some kind of y equals x to the 4th sort of thing. And this looks like it could be some y equals x to the 3rd kind of thing. So that jives with the way that we've been seeing those those polynomial type things working out. All right, so 26, last one. 26A, I've got two horizontal lines with a slope of 0 and then a slope of 0 again. But at 0, there's a jump in this graph. And if there is a jump, you cannot pin a tangent line onto this function. I mean, where are you going to put it, right? You can't, like, put it here. You can't put it there because there's not even a point there. So if a function has a discontinuity, you cannot find the derivative there. If a function is not continuous at some point, it cannot have a derivative. Eventually we'll start saying that it's not differentiable. So here, no, that's a bad example because this is continuous. So it's possible that a function could be continuous and not differentiable. But the converse of that is not true. If something is not differentiable, it could be continuous, but if something is continuous, it doesn't necessarily mean that it's differentiable. That's what I'm trying to say. I think that's converse. Not sure. All right. How about in B? It looks like in B we have something that starts out with a slope around 0, and then they get positive and get like really big. And it looks like it's pretty close to vertical, so that like maybe there'd be like a vertical asymptote there. If you made it go up to an actual point on there, I think I'm okay with that too. And then on the other side, it continues to be very positive. Oops, positive slopes, sorry, so not down there. So positive slopes and then coming back down toward 0 slope. One of the counterintuitive things about all this is looking at these slopes and saying like these are positive slopes. But I mean, if this is a graph of the actual slopes, these are positive numbers. I mean, it's above 0, right? So that would correspond to a function that was increasing. So it's like increasing, but they're just getting smaller towards 0, right? But they're still positive. They're up above the axis. All right, last one, really the last part of the last one. I've got something, it starts close to 0, and they go up getting real positive, like maybe asymptote there, maybe it gets close to vertical, hard to tell. And then it comes back on the other side, they're negative slopes, decreasing. All right, there you go. I think I have a special video somewhere that I'll post. If I say this and then don't do it, you're going to remind me if you feel like you need it. But I think I have a special video. It's a little bit more practice doing this thing, sketching these, if you feel like you need that. Okay? So if you don't see that up in our classroom sometime, let me know. I'll post it.